Okay, so welcome to this week's Origins Colloquium. We're very pleased to have Jenny Green from Princeton giving the talk today. Jenny received her PhD in 2006 from Harvard and was working then with Lewis Ho and Jean Hucre on growth of black holes. She was then Carnegie Princeton postdoc till 2010, and then an assistant professor at University of Texas, Austin, I think just for a year, it says here, and then joined Princeton faculty as an assistant professor in 2011 and is now a full professor there and is leading many activities to understand the origin of supermassive black holes. So we're very excited to hear your talk today, Jenny.
Thank you, Jonathan. It's nice to be talking to you. I can't see you, but I trust that someone is out there listening. So yeah, feel free to interrupt me with questions, and we'll have plenty of time for discussion. This has been one of the most exciting periods in my career, this early JWST data, and really unexpected. I've never worked at high redshift before, and the data are just incredible. So it seems like a once in a career event. So I'm really happy to share some of the stuff we've been finding and some of the things that have been keeping us up at night with these little red dots. In the background here, you see the uncover fields. This is Abell 2744. There's three subcomponents of this massive galaxy cluster at redshift 0.3. And of course, we're interested in the lensed background sources there and the ones that are showing intriguing evidence of being early supermassive black holes. So there's kind of two pieces of context that I want to put forward for my talk. One is what anyone who paid attention to high redshift quasars understood. I had not tuned into high redshift quasar studies prior to the launch of JWST, but what I'm showing here in the pink points, this is from Yoshiki Matsuoka, is that the UV selected, ground-based UV selected quasars are very, very rare, right? There's a few hundred across the whole sky above redshift of 5, which means that in the blue, you see the galaxy luminosity function. It means that unlike every other redshift, if you believe that you found all of the AGN with these UV selected quasars, then you kind of have to posit that most galaxies have not grown a healthy black hole yet by redshift 5 or 6, because we're not finding them in the X-ray and we're not finding them in the UV. And so if you talk to modelers like Marta Volontieri or people who were trying to explain these early quasar luminosity functions, they were actually having to contort themselves to get the black holes to start growing later because of this very rare low number density of UV selected quasars. So that was one pre-JWST context. The second context was a result that made a big splash early in the right after the summer, after the launch of JWST. And there were a number of different versions, but the paper that made the New York Times in some sense was this paper led by Ivo Labe, claiming to find evolved galaxies at redshift 8 with stellar masses as high as 10 to the 11. And we have nicknamed them the universe breakers because there was the discussion that you just simply don't have enough dark matter halos to host all of these massive galaxies. Their number densities seem to be quite high. And so there was quite a bit of furor in the popular press also that maybe lambda CDM is broken, thus the name universe breakers. But then very quickly after, people started to get spectroscopic follow-up of these luminous red things, and at least some fraction of them turn out to be lower redshift broadline sources. So this is a paper that came out, I don't know, 6 months later, early in 2023 from Dale Kochevsky. This is one of Ivo's universe breakers. You see this very characteristic SED on the left. You see a steep rising continuum in the rest frame optical. So H alpha is right there at 444, 4 microns. But then you see this flattening in the UV. So you're going to see a lot of examples of SEDs that look like that. And then on the right, you see a broad H alpha line, so a couple thousand kilometers per second. And this Klochevsky paper posited that this broad line is an indicator of an accreting supermassive black hole. And then soon after, the Sears team, led by Guillermo Barro, put out a wider sample of these things with, again, I don't know if you can now see my cursor, probably not, but
Sorry, no,
what you
it's okay.
Anyway, left-hand plot, those purple and red points are tracing the steep rising red continuum. And then again, this is an F nu, and then just a present but low level blue, a little bit of UV frosting, as we call it. And so this is where my team got involved. I'm part of this Cycle 1 Treasury program called Uncover. The PIs are Ivo Labe and Rachel Bezanson, but there's also a large team of junior people who have been making the catalogs and doing the photometric redshifts. So I just want to call out Sedona Price at Pitt, John Weaver at UMass, and Bingji Wang at Penn State, along with Ren Cease, who's just released publicly the medium band component of Uncover. So I showed you the Abel 2744 field. We had originally 7 NIRCam bands to about 29.5, 5 sigma depths. So from 1 microns to 4.4 microns. Now we go all the way to 070, and we have all of the medium bands as well as those six broad bands. So around the same time that Dale published this first broadline AGN at Redshift 5, Lucas Furtak within the Uncover team, who's one of our lensing gurus, published a paper with this triply lensed source. So you see those 3 red images are all the same object. They're at a redshift of 7. And because they're magnified by something like a factor of 6, the fact that they are completely unresolved puts a very stringent limit on their size. So this source is at maximum 30 parsecs in size. And it also displays this characteristic SED, steep rising red continuum, little bit of UV, additional UV flux. As I said, very compact. Our original photometric discovery paper was really unable to model this SED, but again, to point out the very similar colors to the universe breakers. And so this was sort of the second shoe to drop. Because it was so compact, really, we posited that it might be powered by an AGN. And the picture that we put forward is that red continuum is the intrinsic AGN continuum, but it's been reddened. And then maybe this UV emission could be scattered light from the AGN that is seen quite commonly at lower redshift. Well, it's rare, but it has been seen a number of times at low redshift, or maybe it's just a little bit of star formation. So what we decided to do was look for more of these compact red sources with Uncover. And this right-hand panel shows the primary color selection. This is also what Guillermo Barro did. This is just 277, so 2.7 microns minus 4.4 microns. And if you're red in that color, then you're very likely actually to be a point source in the photometry. And enforcing no spatial extent and these red colors, we came up with a sample of 30 photometric candidates. And this was a paper led by Ivo in the middle of 2023 from the NIRCam data. So these are SEDs just with the NIRCam data on the left, two different compact red sources. And you can see in red is the quasar model that I sketched out for you. So you see the reddened AGN continuum, and then a little bit of blue light, maybe from scattered light at a few % of the intrinsic red luminosity. But you can also see a dusty star formation solution. And that would require star formation rates of something like hundreds of solar masses a year to explain the amount of light that we see. But what you see in the middle panel is that from Seiji Fujimoto, we also have deep ALMA at 1.2 millimeters. And we way rule out dusty star formation at typical 35 Kelvin temperatures from that ALMA point. Of course, you can always make it hotter. So we couldn't rule out 70 Kelvin dust, but we can rule out 35 Kelvin dust. And so what you see in the middle panel is a more plausible model, which is that the red continuum comes from the AGN, so it peaks at much higher temperatures, like 100 Kelvin, and then you can satisfy the ALMA limits. And I should say, right, so that's the dusty AGN point. And just to make this very stark, on the left-hand side, if you do a color selection, but leave out the compact morphology, so you get a lot of dusty star-forming galaxies at redshifts of 2 to 6, which we detect handily in our ALMA observations individually and in the stack. Whereas these compact things where we additionally apply a morphology cut, we have only an upper limit. So stacking all of the 30 sources, we do not detect it at 1.2 millimeters. Right, so that was our original photometric selection paper. And at the same time, Fresco, which is a GRISM survey in the Goods South and Goods North, I think, discovered a similar phenomenon, compact, very red sources, except they had spectroscopy, and what they were finding was broad H alpha. So back to that Klochevsky object, but many more. And it was this Urit Matthew paper that coined the term little red dots, and that stuck. And so we call these compact red sources little red dots. Now, there was a second component of Uncover. We had all of that deep photometry in the Abell 2744 field. Then we went back in August of 2023, and we got 7 deep microshutter array pointings with the prism. So this is a low resolution spectroscopy, which is about R of 50 at the blue side and R of 400 at the red side when you have a point source. And these are the spectroscopic confirmation that the objects we selected to be compact and red, in fact, have very prominent broad lines, broader than 2,000 kilometers per second. I should say we also got 3 beautiful brown dwarf spectra, which was not our intent, but Adam Bergasser was very happy to lead a paper on those. Because they're quite faint, they end up being more likely to be halo objects, so they're quite interesting in their own right. In any case, we did get 12 very unambiguous broadline AGN, and the universe was super kind to us. So in addition to that Tripoli lens source at redshift 7, we also have one of the clearest known broadline AGN at redshift above 8. Vasily Kokorov led that paper. And then an object that we continue to be intrigued by, and what remains the brightest known little red dot. We lovingly call this thing the monster, 4,500 kilometer per second broad line at redshift 4.5. I'll also point out, if we have time, I'll get back to this, that there's this characteristic break in the spectrum, right? Because you have the rising red continuum in the rest frame optical, and then you have this little excess of UV in the rest frame UV, but the break always happens at the same redshift around 3,600 angstroms, and it looks in many cases for all the world just like a Balmer break. So it looks like stellar photospheres. This source again is smaller than 30 parsecs. So here it is. These are our 3 MSA pointings of the Tripoli lens source. So 1 on each image, a total of 38 hours, taking into account lensing. We call this a 1,700 hour near spec spectrum. And you can see that indeed we have extremely good signal to noise on what is a very strange SED. And we still don't understand it, but this is where that 4,000 angstrom break looking thing is, and we'll come back to that. Okay, so on selection, this is a really dense plot. There's just a couple things I want you to take away. If we just think about that original 277 minus 444 selection, so just objects that are red in that color, so very similar to the original Labe universe breakers, 30% of those, based on a spectroscopy with that red cut alone, 30% already are broadline AGN, which is already quite remarkable. If we then add a second color, and the second color just basically gets rid of emission line contamination, So some fraction of objects look red in this color because they have booming H alpha in 444. We get rid of that with a second color, and we add that compactness criterion, then at least 80% of the targets are broadline AGN. So this is a very large population when you restrict your attention to the reddest things in NearCam. So why are people obsessed with little red dots? And the community this has really taken hold in the community. Something like half of the extragalactic AGN channel proposals to JWST had to do with little red dots, which was sad for me because I didn't get my time. But why do we care? Why is this exciting? First of all, they're very numerous. So down at the bottom left, you see those crosses are again the UV selected quasars, which, as we covered at the beginning, are very rare. The squares are the galaxy UV luminosity function, the open squares, and the red squares are our little red dots, our spectroscopically identified little red dots. And so what this is 100 times more by number density than the UV selected quasars, and it is a few percent of the galaxy population, and probably something like 20% of all broadline selected AGN from JWST. On the right, you can see our best guess for the bolometric luminosities. These are certainly not quite as bolometrically powerful as the UV selected things in open circles, but they're healthy accreting black holes, which we think have black hole masses of around 10 to the 8 and bolometric luminosities of 10 to the 45 to 10 to the 46. At least for the most extreme objects in our sample, both the Tripoli lens thing, which has a size of 30 parsecs, and Vasily's redshift 8.5 thing, the nominal ratio of black hole mass on the y-axis here to galaxy mass is extraordinary compared to local observations. So 1% or more of the baryons that we can see seem to be in the black hole. And because this particular thing is at redshift 8.5, you're also really pushed into a corner in terms of how you can grow that black hole. So if you limit yourself to Eddington accretion and you start at 100 solar masses, you just ain't gonna make it. So you either have to relax the Eddington limit or you have to start with a more massive C black hole. Not only that, but having the host galaxy be rather anemic compared to these black holes also pushes you into this scenario where you kind of need the black hole to start before the galaxy really takes off, because anytime you supply gas to a galaxy in a black hole, you would expect the galaxy to grow more efficiently than the black hole, right? Because the gas has to lose a lot of angular momentum to fuel the black hole. So this is, I'll talk later about the extent to which this could just still be a selection effect. Of course, we're selecting things to be compact. But as I said, the number densities of these little red dots is high enough that we are pushing into an uncomfortable part of parameter space, if we can believe the black hole masses. Okay, so now is where you get into the things that we don't understand and the things that keep me up at night. So just to return to this question of, can I imagine an underlying normal population of galaxies and black holes with a similar underlying scaling between the galaxy mass and the black hole mass, but if I just put enough scatter in, are the little red dots sort of the tip of the iceberg in terms of the highest black hole to galaxy ratios? And that's the pink model here, which was built by Marta, basically by populating galaxies and black holes into dark matter halos in order to explain the little red dot results. Things are most dramatic in our higher redshift bin around redshift 7. But what you see is that we can nominally explain the number densities, even preserving an underlying normal local black hole to galaxy scaling relation. But you have to invoke high scatter, and you can only just barely do it. Okay, so you get to a point where many of the black holes need to be radiating all of the time as little red dots. But there's some other observational problems or things that we don't yet understand that make me wary to think we yet understand what the black hole masses of these things are. So this is a complicated figure. This is just the standard spectral energy distribution of AGN, of accreting black holes. The blue line is the UV, the big blue bump. So that's the optically thick, geometrically thin disk that powers the AGN. And then, of course, some large fraction of that is re-emitted in the mid to far infrared as hot dust. And then finally, of course, you have a corona that makes X-ray. And I was raised that all black holes have X-ray emission, especially at hard energies. And most black holes show this rising hot dust in the rest frame mid-infrared that is the signature of a black hole. So the little red dots do neither hot dust nor X-ray. This is a stack of the photometrically identified little red dots from JADES. This is Christina Williams' work. They have all of the Miri bands in this SMILES program, and so she stacked them. And you can see the orange line is the expected SED, the hot dust that we expect if the little red dots are AGN, which is basically just they're red in the rest frame optical. You would expect them to just keep on rising. They do not do that. They turn over and flatten in the mid-infrared, and that is true across all fields. It's true for spectroscopically identified things. So it seems to be universally true for little red dots. Also, there's now been a spate of papers pointing out again that there are no X-rays from these things. So in Abel 2744, we have lensing on our side, and we have 2 megaseconds from Akush Bogdan. We do not detect our sources in the X-ray. This is rest frame 40 keV X-rays because we're at redshift 5 to 7. So they have to be extraordinarily Compton thick to describe this from absorption. Seems likely to me, at least, that they are intrinsically X-ray weak. Or in my darkest moments, that there's no black hole there and the broad lines are coming from something else. So this is our problem. This is one example that was.
Can I ask Jenny just a quick
Yes, please
question?
do.
So the main reason they are red in the optical is because of dust or not?
I mean, that is our best guess, but we don't know.
But then they don't have a lot of other dust that continues that you'd see in longer wavelengths.
We do not detect them between 3 and 5 microns rest frame, where almost all AGNs show 1,000 Kelvin dust. We do not detect them. I mean, here's a source where we detect it. We don't detect the hot dust. So it looks just like a continuation of an accretion disk model here. Those are
so you sort of have
two reddest points are the Miri points.
So you have your big blue bump, but reddened to make the main.
That is what this model is. Yes, the red line is a reddened big blue bump with an AV of 2.5 or something.
Okay, great.
The expected torus is the pink line. Just vanilla torus, vanilla temperatures, that would be where it would be. And these are the Herschel limits, which are not that constraining.
Okay, great. So sorry to interrupt. Please
No, that's fine. It's fine. So this is from Bingji Wang. So this is one example where we have spectroscopic confirmation and we detect it in Miri and we do not see the hot dust. And then finally, last perplexing thing is this eerie confluence of strong breaks and broad lines. And so, when Evo wrote that original universe breakers paper, they thought they were detecting a bunch of 4,000 angstrom breaks at redshift 8, evolved stellar populations and very massive. Now we actually have a bunch of spectra for those original Sears detected universe breakers. And the crazy thing is that they do all have breaks. So this is a stack of their 4,000 angstrom breaks. And they all have broad lines. So it's a yes and situation. They seem to be slightly and possibly massive and evolved and have broad lines indicative of AGN. So there we are. My student Elon has been trying somewhat desperately to fit, this is the triple lens spectrum now, jointly model the AGN and the galaxy. This is his current best fit, although we've been getting increasingly desperate. So Jonathan, you asked if the picture is that they're intrinsically blue, but Dusty, here's where we've tried with a super Eddington model, which is intrinsically much redder. Still need a little bit of dust, but you can make the intrinsic AGN power law redder, and that does alleviate some problems, but then, you're totally galaxy dominated until right under H alpha, where it becomes about 50-50 in this particular fit. And this is really, really pushing up against the boundary of stellar densities that we've observed today and the age of the universe, because this thing is 30 parsecs or smaller at a redshift of 7, and we're stuffing 5 times 10 to the 9 stars in there to reproduce this break. So a little bit uncomfortable, not impossible. Finally, kind of fun. This is, again, our friend the monster. This is now spectra from ALT. So this was work done by Ivan Kramarenko in collaboration with Yorit Mathy and Rohan Naidu as part of their ALT survey. This is a GRISM survey in the Uncover field. All of the blue points are associated with an overdensity in which our friend, the little red dot monster, also resides. That's the red circle. So that's a pretty big overdensity at redshift 4.5, but quantifying overdensities is kind of a black art that I'm not so good at, but lots of galaxies there. So it's probably a protocluster of some sort. And then finally, I didn't talk about this yet at all, but at least in about a third of cases with high resolution spectra, we see narrow absorption features in the Balmer lines, which are hardly ever seen in lower redshift quasars. Very, very occasionally do broad absorption line quasars show absorption in the Balmer lines, and it's usually taken as an indication of very high densities. So we see this helium-1 absorption in the big red dot from Bingji's paper. The Fresco paper from Yorit showed, a third of the cases show this absorption. We now see it in this friend. So I don't know if you can see, but this is its broad H alpha as seen by ALT. And then we see these two dips. I originally thought that was the nitrogen 2, but no, the nitrogen 2 is way out here. This is absorption right at this close to the systemic velocity. Okay. And so the kind of existential question for me now is, can I continue to support this AGN model, which is mostly, the biggest argument are these whoppingly broad Balmer lines that I don't really know how else to explain. This is 10 to the 44 ergs per second of H alpha here that you would have to explain some other way. Or should we imagine that they're powered by stars with some other explanation for the broad lines, and then it's natural that we don't see the X-rays or the hot dust? So that's where we are. I think I will.
Jenny, could I ask a question?
Well,
Please
great.
do.
Let's thank. I think you're at the end now, are you, Jenny?
Yes, I can put this up as my summary. The high number densities, the high black hole to galaxy ratios, and the uncomfortably early growth. Yes, please.
Great. So let's thank Jenny first. So thank you, Jenny, for a great overview. And then, yes, Mark, I think we can just go ahead to the questions now at this point.
That I can see people now, is that?
Can you see us?
I see you, yes, and I can, you all see me, I assume.
I do, at least. Yeah, I think we do. So great. And of course, you feel free to come back to your slides in the discussion.
I can show my slides again. If
yeah. So I have lots of questions, but we'll go ahead then. Mark, go first, please.
Okay, thanks. Sorry, Jenny, to coming right on your very last statement. I didn't mean to interrupt there.
No, that's totally fine, totally fine.
Okay, and actually fascinating talk. And I think I'm wondering whether you have enough forbidden lines to do versions of the BPT diagrams, which of course are usually used to see if there's any non-stellar ionizing continuum. And I don't recall you addressing that. Could you summarize that?
Well, so the reason, I guess there are two reasons I have not plotted that, but the data reason is that the prism resolution is very, very low.
Yeah,
and I would say that my constraint on the narrow H alpha is either poor or non-existent, depending on, so for instance, that's the source I showed you, the GRISM spectrum for just at the end. That's high resolution GRISM data. And there is basically no way of teasing out a narrow line with that absorption there and such a broad emission line.
Gotcha.
And we don't detect the nitrogen 2 at any significance in that source, despite the fact that in order to explain the break we see, it needs to be a 10 to the 11 solar mass galaxy. We don't have high resolution O3. We do detect the O3, it is narrow. So the O3 piece is fine, but I can't really do the H alpha and the H beta.
Right. Okay. Yeah.
And so it just didn't, the O3 over H beta goes all over the place. I don't know if you saw. It says I'm still sharing. That's weird.
Yeah, you showed, I mean, the nice list of spectra that you showed had a few O3 to H beta, which looked AGN-like to me, but I couldn't
Let
see
me
them
just
carefully.
quickly show you what's the best view of this. This probably is the best view. So this is our, our triple lensed. You see it now? Maybe?
Yep.
Great. I'm not going to go back into slideshow, but that's the O3.
Ooh, I see. Yeah.
So that's
Yeah.
very, very weak. It sort of looks, I mean, like a narrowline C4 in this particular case. In most cases, the O3 is quite prominent, but it is completely blended between the two. I mean, you're probably not used to looking at prism spectra, but the
No,
resolution
that's okay. That's right.
dramatically as you go towards the red. And so that's the H beta and that's the two O3 lines blended together. So we detect O3, but like I said, I can't really tell what is what with the H beta or the H alpha.
Right. So that might be, I mean, an important goal for higher resolution spectra then to try and.
Yes. Yes.
do that.
There's some
Okay, thank
coming.
you.
Hannah Ubler has an IFU program, and so does Yorit. So we'll have some high resolution spectra coming in cycle 3.
Gotcha.
So
Thanks, Jenny. Thanks.
let's come to the question then about you mentioned that maybe you have this scenario where it's sort of star forming systems, but I may, obviously there's a number of problems with that. This issue of compactness, for example, when you stack them, or do they remain compact, or do you see faint extended emission from a host galaxies from a host galaxy?
So in 444 they are point-like, but in the UV actually we often do see a little bit of fluff. I don't know if any of these examples are good. No, but let me see if I can show you the one benefit of being in a virtual environment.
So there is some star formation, that there's some distributed UV.
It seems that there is some star formation, yes. And again, technically you could probably model it as scattered light, but almost certainly it's star formation here. Let me just, this is the 070 image of the monster. You see it's actually quite extended in 070. So that's rest frame UV. Can you see it? Yeah. Whereas in 444, the resolution is much lower and it's much redder, and it is, you see diffraction spikes. It's totally unresolved. Yeah.
So I'm trying to, so there is some star formation, but it would be difficult to make all of the emission from star formation, it sounds like.
Well, they are very faint in the UV. They are 27 to 28th magnitude in the UV. It corresponds, if you just take it at face value as star formation, it's a few solar masses a year. If you imagine that it's all buried star formation in order to explain all of the red continuum, you're talking about a couple hundred solar masses a year of star formation, very little of which is getting out in the UV, and that's fine. But then it really needs to be quite hot because we don't detect it in ALMA at all.
Right. But I'm trying to remember now how this works. So the flux at 1.3 millimeters, so even if you make it hotter, is it really going to
basically the peak? It's basically the peak of a 35 Kelvin modified black body at these redshifts.
I guess I'd have to see some SEDs, but so you have,
I mean, here they are, right?
You'd have much less, you're saying you have much less dust, but it's hotter.
I mean, this is our 1.2 millimeter limit. And in light blue is just a naive template, star formation template, which matches the rest frame optical. It's orders of magnitude higher. So you have to shift the temperature by quite a lot before you don't pick up the tail of that thing.
Right.
So at 100 Kelvin, you're fine. But it really has to be quite hot.
Very good. Are there other questions? Raise your hand in the Zoom or Joe, that you're at the Chalmers room, you can moderate there. I have plenty of other questions here. Let's see then. We went while we're on the dust then. So you do need some reddened. You need some dust to redden the blue bump. But I'm trying to.
Right.
The blue bump is a photosphere of around a few thousand Kelvin, isn't it? But at least or more. So isn't it? So
The big blue bump?
Yeah.
We typically think of it peaking in the near UV for a 10 to the 8
Yeah.
solar mass black.
So it's hot. So the dust is a sort of foreground dust, is it? Because the dust would be destroyed in
That is the idea, yes. In low redshift, reddened broadline AGN are mergers. And so you're seeing through to the broadline region, but there is some dust screen in the way.
right.
In
But
this case, they're not mergers, or if they are, they're on very small scales. So why you could have AVs of up to 4 and still see the broadline region, but not see the X-ray and not see hot dust is a puzzle.
There's basically a foreground screen of dust you'd expect to be more extended than
I mean,
the source.
there could be an extended gas component that is just not bright in stars. That's more extended than the stellar component, for sure. I cannot rule that out.
Mm-hmm. So the ALMA
have very little dynamical information either.
Mm-hmm. So there's no size constraint from the ALMA data or one that's much larger.
There's only upper limits from ALMA, even when we stack them all. We do not detect it in ALMA.
Mm-hmm.
I mean, we put in a lot of ALMA proposals to go to higher frequency, so we certainly have hopes to detect them in ALMA.
Yes.
But we haven't yet.
Okay. Other questions from the audience? Let me ask, going back to the first system you mentioned, the triply lensed, what are the time delays on that system? Do you have a sense of?
We don't have robust measurements of that. We know it's been around for at least 20 years because it was actually 2 of the images were detected in HST.
Yeah.
And it's high on Adi and Lucas are desperate to find to get variability information, but we don't have
Right. I mean, how would you?
I guess you have to monitor it, right? It's pretty faint. I don't know how you would do it. They wanted to try and look at differences in the different spectra, which were taken at slightly different times, but given how challenging it is to just flux calibrate the spectra right now, we decided that was premature.
Yeah. So, but if and the lensing is not certain enough, of course, that you would really need to monitor it.
I think so.
But you said HST detected them before.
Yes. Yeah.
So that must be a few years earlier, is it? Or
yeah, so these are Hubble frontier fields. So I think it was detected at 160, I guess.
Well, maybe maybe we can have there's a few of us in the call here who are particularly interested in the variability aspects, so we might be able to follow up with you on that. Let's see then. Okay, Mark has another question. Good, Mark. Please go ahead.
Yeah, sure. Thanks, Jonathan. So Jenny, I'm just looking again. I took a snapshot of the spectrum of the lensed source, and I'm seeing that you're labeling iron 10 sort of 63.
Oh, I think
sort of 60 rest. Is that an ID? I mean, if it is, that's sort of slam dunk, really, I think, for AGN, maybe. I'm not sure that's quite fair. It's
my feeling is that so we do detect the O3 and we detect hydrogen lines, and that would be all I would believe. Lyman alpha, H alpha, H beta, H gamma. I don't believe the iron 10. I think there was a flurry of activity about whether it would be some other line.
Well, oxygen 1 is very close, right? I mean, 6,300.
6,300, right. We don't detect, there's 2 of those, aren't there? I don't think we detect the second one.
Yeah, 6,300 and 6,364, and then the iron 10 is just in between them.
In between, right. The resolution's not great. The stacking is uncertain. I think we just need higher resolution data before we start to try to do that.
Okay, all right. So in other words, that label
We probably
It's
shouldn't
not
have
an
done that.
ID. It's a sort of speculation.
Aspirational, yes, I would say
Yeah,
so.
okie doke. Right. Because that's very important. I mean, if it was iron
If
10,
it
I
were
think.
real, yes, I would not trust that myself.
Okay, all right. Yeah. Thanks.
Yeah.
But in summary, though, I mean, AGN seems very, it has to be AGN with the broad lines and the compactness. I mean, I just don't see how anyone could really.
I mean, I certainly think that is the most natural explanation for a lot of their properties. Yes.
So
Also the high stellar masses. I
Mhm.
mean, what the follow-up spectra of the universe breakers show a 4,000 angstrom a Balmer break.
Right.
But the
So let's
stellar
accept
mass goes
them.
way
Yeah.
down if you add an AGN continuum, and that just seems much more natural. Otherwise, you're starting to really
Right.
make a lot of stars very early.
Yes. I mean, let's accept them as AGN then. So now you mentioned about how well we can infer say the black hole mass or accretion rate. Perhaps you can say a little bit about the degeneracies in the SCD fitting, or is there any
I would say that we, to zeroth order, if we can't understand why we don't detect them in the X-ray, particularly, I mean, we have lots of stories about why we don't detect the hot dust, like it's higher optical depth, so the whole torus gets colder. There are cold torus models. The whole thing is shifted into a little bit redder, fine. But no X-ray at 40 keV says to me that we really do not understand the SED. And what we're inferring to be the bolometric luminosity could in fact be wrong by more than a factor of 10, maybe because they're super Eddington, maybe because we're misinterpreting the redness. I mean, so, roughly speaking, our black hole masses are putting them at 10 to 30% Eddington, normal everything.
So there's no local example of an
I don't
AGN?
think we can know that. Say it again.
There's no local example of an AGN like this without the X-rays with such an SED?
There are X-ray weak AGN. There are a small subset of AGN that don't have hot dust. There are so far no known little red dots at low redshift. There's one in Jades at redshift 2.5, spectroscopically identified by JWST. But also there are very few objects that are this X-ray weak, period, in the universe. I mean, there are X-ray weak AGN, but usually we detect the X-ray eventually. They're just X-ray weak. Now we are having population level stacks where we don't detect a single X-ray yet. And again, it's rest frame 40 keV.
So if I'm no expert on the X-rays from AGN, but it's from a corona. I mean, if they're very actively accreting and there's a strong outflow, doesn't that?
Yeah, that's the things that people usually wave their hands about to get rid of the X-ray. Yes. Either super Eddington so that there's advection in the inner part of the accretion flow, or some very vigorous wind that either starves the corona of UV photons so you don't make a corona, or blocks the X-ray very locally. Those are the kinds of models that people have for X-ray weak things. But usually some fraction of a population are X-ray weak, but we are talking about no X-rays ever detected from a little red dot, which makes me think that our overall expectation of their luminosities is wrong. But I don't know. I mean, I don't know. I just don't think we can trust the black hole masses as taken at face value, and we really truly cannot explain the SEDs.
So the black hole mass though comes from the SED or comes from the line? Is the line width affecting it at all?
Yeah, it comes from the line width and a luminosity that's been dust corrected. So if you take the broad line and you take 5,000 angstroms to 6,700 angstroms, and you just imagine that it's a normal AGN at redshift 1, you can get a black hole mass the way we have been doing for 20 years. And that's 10 to the 8. I mean, 10 to the 7 to 10 to the 9, but typically 10 to the 8. Right. But I think everything would be much more comfortable if they were an order of magnitude less massive, a little bit super Eddington, and that's why they're red. As an example of one way out, that alleviates the scaling relations, it alleviates the number densities, it alleviates the early black hole growth, and it alleviates the X-ray. So I like that in principle, but nobody can give me an SED a super Eddington SED that I could really compare with across all of these wavelengths. Like that's just not a thing. So I don't know what to do next to verify that or test it.
Mm-hmm. Okay. Mark again, please.
Yeah, Jenny, different kind of question now. I think I didn't quite follow your introductory slides, which talked about the sort of space density and so could you just help me understand now the number densities that you're finding here, whether they jive with the number densities of other surveys of quasars at high redshift, and also, of course, the question of whether the duty cycles are such that you can then populate all of the, zero redshift galaxies with black holes, whether or not they're accreting. So it's the demographic question, I suppose. Do they jive with our other understanding of the demographics of AGN?
So this is the luminosity functions, and I will say that all of the surveys get the same number densities. So we have to do a lot of contortions because of lensing, but everybody gets the same answer. And we're still in UV luminosity space, which is terrible for the little red dots, but that's what everybody at high redshift does. So that's what we're doing. Okay, so we are about a factor of 100 times more common than the extrapolation of the UV luminosity functions, UV quasars from the ground. We are a few percent, 2 to 3% of galaxies at a given UV luminosity. And we are, and this is the least certain, but we're something like 20% of all of the broad lines that have been selected with JWST. This is Harakane and Malino. So that's where we are. Quite numerous. Now, to your second part of your question, this is what this figure is trying to address. So the black line here is if you take every halo and you give it an AGN above 10 to the 44 in bolometric luminosity, that would be the number density that we would get. That's why we call it the maximum model. This is a truly duty cycle of 1. We are lower than that, so that's good. We're not breaking anything in that sense, but we're not that far off from something that seems completely crazy. That's really a duty cycle of 1. So we're only a factor of 10 below that or less. Right? And that's why, again, it really matters what we say the bolometric luminosity is. If we shifted them by an order of magnitude lower, we'd be totally fine, right? If these were living in lower mass halos and they're just popping up as super Eddington, it's no tension at all. But if we take everything at face value, like I said, like we do with the low redshift, then we're really pushing. We're right at the edge.
Okay, great. Thank you. Yeah.
Well, we are developing models in our group, Jenny, that try to explain these luminosity functions. Maybe Barry can show something later if we have some sort of more informal time. I was going to ask about the multiplicity. Do they all appear? They all appear as single objects? Is there any hint of? I know Myelino has claimed 1 or 2 potential multiples.
Well, that's not. That's just because he sees 2 velocity components in the broad line. It could also be a little bit of absorption. This would be our preferred explanation for those. But
yes, I agree.
Well, they are unresolved at 444. And with the lensing, that means the whole stellar system at 444 is smaller than 100 parsecs across the uncover object.
Yeah.
We do see them in dense regions, and there's a couple objects in Fresco where there are 2 little red dots that are clearly at the same redshift, but we see some UV flux, but we don't see companions very often at our depths.
Maybe
1 or 2.
When you say there's a pair of little red dots, how close are the pair of?
Oh, I don't know. Not within the same halo, but I don't remember exactly what the distance is. They're not merging or anything.
Okay. Let me see if I have other. Okay, I was going to ask you because Jenny, you obviously worked a lot in the low mass end of AGN in the past, and I wanted to get your thoughts on happening in that field. I don't know if you know, the, basically,
Well, I mean, I think all of these, our ability to select large numbers of broadline AGN, at least down to 10 to the 6 already in whatever it is, 2.5 years of operations of JWST, suggests to me that we are going to be pushing into a regime where we're really starting to understand about seeding mechanisms, actually more so than I somewhat curmudgeonly expected with pre-JW data coming. So I feel quite positive. John Chisholm has this paper where he detects a neon 5 line in a 10 to the 9 solar mass galaxy. Really, really strong neon 5, very hard to explain with any stellar models. And he does the
That's a
stellar
nearby
models.
galaxy, is it?
No, it's at redshift 5.5.
Oh, sorry. Well, I was more on if in the study of the more the local universe, if there's evidence, well, in the past, this absence of black holes around 10 to the 4 solar masses, whether it was they were just too faint to be seen, but I don't know if James Webb is making an impact also, and
locally, I know Shobita is trying. I think it's hard to get the kind of samples that you would need at redshift 0. My guess is that the place to look is redshift 2, where we can get big samples of low mass galaxies cheaply, and then maybe, look for various indications of AGN activity, X-ray, mid-infrared, whatever. All the way down, we have complete samples down to 10 to the 8, easy peasy, redshift 1 to 2. But I don't think JWST is going to be super helpful locally. It's just too hard. Certainly dynamics, it's not built for that. It does not have the spectral resolution. We can't do it. But in terms of accretion, you're going to have to look at hundreds of objects before you find a couple AGN, and that's just not a JWST thing, really. Maybe for follow-up, multi-wavelength follow-up, perhaps, but I don't think it's going to be a discovery machine. At least I haven't figured out how to do that. I'm more excited about LSST and tidal disruptions and things like that as breaking open new discovery space at low redshift. I think that's the next big thing for us.
Very good then. Are there any last questions for Jenny? Okay, if not, let's thank her again. I'll stop the recording.